We had covered the thermal efficiency of heat engine. That means the evaluation criteria of how good a heat engine is or how bad a heat engine is performing is thermal efficiency of a heat engine. Similarly, we have also looked into the um, coefficient of performance of refrigerator and heat pumps. Again, the two parameters, the COP of refrigerant and COP of heat pump, reflects about the quality or the performance of a specific refrigerator or a heat pump. These are the evaluation criterias. But coming to the point, we will be moving on towards reversible and irreversible processes. But in order to understand the need of having a reversible and irreversible process, we need to understand why do we need to have a reversible and irreversible process in the first place. The second law of thermodynamics, it states, so far what we have seen, it states that no heat engine can have an efficiency of 100%. This basically means that whatever heat you are getting as a source, you cannot convert 100% of it into work. This is known. But the question then comes to the mind that what actually is a possible percentage that you could convert into work, which basically sets the upper limit of your heat engine. Although theoretically or it may be an idealized value, but there should be an upper limit that this is the maximum that you can convert from the heat that you're receiving into work. This could not be 100%, but there should be some value, which is the benchmark value from which you can compare that how far are you from achieving the best possible you can. So again, the questions come, what is the highest efficiency that a heat engine can possibly have? It cannot have 100%, but what is the possibility? What is the maximum possibility that a heat engine could have the efficiency? Before we could answer this question, we need to define an idealized process. And the idealized process, we call it as a reversible process. So remember that a reversible process that we'll define in the coming slides, the features of the reversible process, it is basically the idealization. There is much to imagination to this reversible process as compared to the actual process, which is an irreversible process. So in order to understand the idealized process, let us first understand what an irreversible process is, or how do we say that a process is irreversible. Reversible and irreversible, there are two ways of taking any system from one state to another state using any process. Let's say I have a piston cylinder assembly. I have a piston over here, and there is some gas particles that are within this piston cylinder assembly. The piston cylinder assembly is such that the outside is insulated, so there is no heat flowing outside the system. This is the initial system. At the initial stage, my pressure, volume, and temperature, they are known to me. And if I have a PV plot, I can say that at initial state, my volume is this, and the corresponding pressure is this, PI. Now, I apply force onto this piston and compress this piston cylinder assembly or the gas within this system to a final position, which is represented by F. And I did it in a fast manner, such that I have achieved a new state, which is the final state. I know at this final state, my volume is this much. So I have a specific volume VF for the final stage, and correspondingly, I'll have a pressure at the final stage. The question that comes to my mind is that once I am compressing this, let's say I am at this stage during the initial and final stage, I am some stage A at which there is some specific volume of my system. But since I am doing this process very rapidly, the pressure in this region might not be the same pressure in this region. The molecules in this region may be much compressed as compared to the ones over here, to which the fast force which is being applied is not being transformed as yet. And before the molecules could experience this force, the system has moved from the position A to position B. In other words, let's say for this volume V, when my system is at state A, volume V, let's say it is some volume over here, which corresponds to state A. But since the system was moving so fast, I cannot say whether my pressure in the system was this pressure, this pressure, this pressure, this pressure. I cannot represent the process on the diagram as my system was not having a uniform single pressure. There was a pressure distribution within the system, and since there is a pressure distribution within the system, you cannot say that your system is in equilibrium. However, on a PV diagram, the only states that you can define are basically equilibrium states. In other words, you cannot define for all the states between I and F, for all the states that exist between initial and the final state. You don't know the exact states, so you cannot draw a path from initial state to final state, whether you went this way, this way, this way. What was the process path? You cannot develop that on a PV diagram. In simple words, you cannot plot a continuous graph for an irreversible process on a PV diagram, specifically because your system does not remain in equilibrium at all times. Again, you don't know the pressure or temperature at all points to associate with the volume change. In other words, for an irreversible process, system passes from equilibrium state I, that is an equilibrium state, to an equilibrium state F through a series of non-equilibrium states. This is where your process becomes irreversible. So a quick compression or a quick expansion is a process which is recognized as an irreversible process. Remember that fast expansion or fast compression, it is considered as an irreversible process. Now, moving on, before we try to understand what a reversible process is, irreversible process is that which is not reversible. Not reversible in the sense that if you try to reverse the process, you cannot do so without leaving a net change on the system and the surroundings. This would be a little difficult to digest at the moment. An irreversible process is not a process which cannot be reversed. For example, you have a soda can at 25 degree, at 2 degrees centigrade or 5 degrees centigrade. You place it in your room, it would ultimately get to the room temperature of 20 degrees centigrade. Now, this is an irreversible process, but not in the sense that you cannot bring this soda can back to 5 degrees centigrade. You place it in the refrigerator, it would come back to 5 degrees centigrade. The process cannot be reversed without leaving any net change on the system and the surroundings. There has to be an effect or on the system or the surroundings in order to reverse the process. We'll see how we define this reversible process a little more in detail. First, look at the cause a process which causes the causes which make a process irreversible. These causes are defined as irreversibilities. Some of the few common irreversibilities include friction, unrestrained expansion of gases or sudden expansion of gases, heat transfer through a finite temperature difference. That means heat transfer is not a irreversibility, but when heat transfer is taking place through a finite temperature difference. Although heat transfer is defined due to temperature difference, but when heat transfer is taking place due to finite temperature difference, it's an irreversible process. We'll see how. Mixing of two different substances, electrical resistance, inelastic deformation of solid, chemical reactions, mostly related to uh, mechanics and chemical reactions. So I'll not discuss these four of the mechanisms, but we'll see friction, unrestrained expansion, and heat transfer as the irreversible process, and we'll try to understand how these processes are irreversible. Number one, friction. You have a gas contained within a piston cylinder assembly. Now you are applying certain force or work is being done on this piston. There is work into the system so that the piston move downwards and the gas gets compressed. The gas gets compressed to a smaller volume. As the piston is moving along this piston cylinder assembly, at this point of contact, friction exists, and as a result of this friction, heat is generated, and at heat gets transformed from the system to the surroundings as a result of this friction. So some portion of this work actually transforms into heat, which has not affected your system, which is not being accounted for the change in volume of the system. The change in volume of the system is not entirely to this work done, or it is entirely due to this work done, but a portion of this work that you have done has converted into heat. Now, if I remove the outside load that I have applied or force that I have applied in order to compress it, the system could again move back to the original condition. But as the system is moving back again, the energy stored within the system, which will do the work done, would some of the energy would again get wasted as a result of friction between the piston and the cylinder and would again convert into heat. So essentially, there would be these two heat losses which cannot entirely convert back to work. The heat losses due to friction, you can never convert them back entirely to the work that was used to create this heat. This is the loss that you can not recover entirely. So this is an irreversibility of a process. This becomes the, although the system would come back or can come back to its original position, but this heat that gets lost, you cannot convert it back entirely into work. As you already know, heat cannot be completely converted into work again. So this heat basically is an irreversibility in the system. It's a permanent effect that would remain within your surroundings. Now moving on to the second effect, again, fast compression, fast expansion, you have already seen. Let's say unrestrained expansion. You have a gas which is being separated by a membrane. On the other hand, you have a vacuum. It's at 700 kilopascal, and there is some temperature T of the gas. The moment this film gets ruptured and the gas has to expand in vacuum, what would happen? The sudden expansion would cause a decrease in temperature. The temperature would go down. Now, if you want to make system back to its original position, you will have to compress the gas back to its original pressure, and as a result of this compression, the temperature of the system would go up. This temperature would cause a result of heat transfer from the system to the surroundings, so there would be heat loss to the surroundings. Although the system would come back to its original pressure and temperature, but due to the work done on the system, there would be some heat loss, which again cannot be recovered. This is an irreversibility which you cannot convert back completely to work. That means you cannot bring the surroundings back to the original condition. There has to be a permanent effect on the surroundings in terms of the heat loss to the surroundings. The third thing is, so now you have these two, friction present, irreversibility. Unrestrained expansion of gas, irreversibility. Heat transfer through a finite temperature difference. You have the soda can at 5 degrees centigrade. You place it in a room where the temperature is 20 degrees centigrade. There is a finite temperature difference between the system and the surroundings. Heat would flow into the system and take the soda can from 5 to 20 degrees centigrade. This is a heat transfer which is taking place through a finite temperature difference or due to a finite temperature difference. As a result of this, your system has moved from a lower temperature to a higher temperature. Now this is possible, exactly possible, that you bring the soda can back to 5 degrees centigrade from 20 degrees centigrade. You can do that from 20 degrees centigrade. You could bring it back to 5 degrees centigrade. Your system could come back to its original position, but In order to do so, you have to do the refrigeration process. When you do the refrigeration process, certain work input is involved. There has to be involved some work input for this system to get back to 5 degrees centigrade. That means the refrigerator, if it is outside, it is acting as surrounding for this can. Refrigerator is acting as a surrounding for this can. The refrigerator has to do some work in order to convert this system back to its original condition. This work done by the surrounding is a net change in the energy of the surroundings. Energy has to come from the surroundings. By surrounding, I means anything outside this can. So the surrounding has to do some work onto this soda can, or has to provide some work onto the soda can so that the soda can come back to its original condition. Now, it's clear that soda can move from 5 to 20 degrees centigrade and then it moved back again to 5 degrees centigrade. The system, which is your soda can, gets back to the original condition. But are the surroundings back to the original condition? No. There has been work in that has been involved, which was which is unaccounted for. Since your surroundings cannot come back to its original condition, you would recognize this process as a irreversible process. The smaller the difference between the smaller the finite temperature difference. If this difference is very small, infinitely small, heat transfer through an infinitely small temperature difference, the irreversibility gets so minimum that you recognize the process as a reversible process. And the other way around, soda can, as it is going from 5 to 2 degrees centigrade by releasing heat to 20 degrees centigrade, this is an impossible heat transfer process. It cannot occur without the help of the refrigerator. So in order to do that, you have to have a refrigerator. Clear enough so far? Is it clear?
Yes, sir.
Yes, sir.
All right. Now moving on, let's see what a reversible process is. How do we say that compression or expansion could be a reversible process? Uh, you have again the same system insulated, so there is no heat transfer involved. Heat transfer, when it is involved through a finite temperature difference, the process becomes irreversible. So we have insulated it. You have again the piston cylinder assembly, gas particles within the piston cylinder assembly. Initially, pressure is PI, volume is VI, temperature is TI. You start putting grains of sand on top of the piston one by one. Since the temperature remains same, the system is adiabatic, so there is no heat transfer. The system gets compressed from initial state to the final state, PF, VF, and TF. And you have number of grains present on top of it. But you have compressed the gas exceedingly slow. When you are doing so, you are basically making the system move in an equilibrium manner. The second assumption that we have assumed is, in order to say that the process is reversible, we say that we have a frictionless piston. So the frictional losses are ignored, or we assume that the piston is essentially sliding along the walls. This would make your process reversible. Again, that's an idealization. A reversible process, always remember, an ideal process. So you have, as you're compressing, your volume is decreasing, your temperature is increasing only slightly. So your system departs from the equilibrium very slightly, or in a very small quantity. States through which the system passes are very close to the equilibrium states, and there could be a continuous graph that can be plotted for the two states, initial and the final. Differential change in condition will reverse the process. So example, if I take two grains of sand out of here, it would come back to its previous position without having uh, any permanent energy uh, transferred to the surrounding or lost in the form of heat, which cannot be recovered without any change in the surroundings. So this process becomes a reversible process. Now, reversible and irreversible process. Reversible process is a process that can be reversed without leaving any trace on the surroundings. This is the most important thing. Both the system and surroundings return to their initial states at the end of reverse process. If you remember the soda can, although the can would come back to its original condition, but the system would not, but the surroundings would not. Why? Because the surrounding would have to do some work in order to get the system back to its original condition. During a reversible process, the system passes through series of equilibrium states. You've already seen that. A reversible process actually do not occur in nature. Again, remember the fact we are referring to an ideal process. They are merely the idealization of actual processes. Having a frictionless piston is an idealization. You could get close to that idealization, but again, a frictionless piston remains an idealization. But why do we need to have that? Reversible process can be approximated by actual devices, but they can never be achieved. As I mentioned, a frictionless piston is an idealization. You can get close to it, but you cannot achieve it. So why do we bother about fictitious process? What is the need of having study a process which is actually not possible to achieve? The reason being, number one, reversible processes are easier to analyze. How? Let's say we have seen the PV diagram, initial state to final state, your system moved. This is the reversible process path. Now, if I have to determine the work done, I know the path, the area under the curve would give me the work done. This is for a reversible process. An irreversible process, you have initial state, you have final state. You don't know the path, whether this was the path, this was the path, this was the path. How would you find out the work done? It's all very hectic. So the reversible process makes the system easier to analyze. And they serve as ideal models which the actual process can be compared to. That means uh, if I have a frictionless piston, what is the maximum amount of work uh, that I have to do in order to compress the gas? Or what is the maximum amount of work I can get if the piston starts moving upwards or it's an expansion process? So it, it provides a basis for comparison with the actual processes. In case of turbines are basically work producing devices, and compressors, they basically require work is required. So in an ideal world or in an ideal process, do you expect turbine to have maximum work produced or minimum work produced? Ideally, if the process is taking place ideally, what do you expect? A turbine would produce maximum work or minimum work?
Maximum works.
Very good. So, so the work producing devices such as car engines, gas, steam turbines, they deliver most work, that is maximum work, and work consuming devices such as compressors, fans, and pumps, they consume least work when reversible processes are used instead of irreversible process. That means when they are operating or when the process is taking place in an ideal manner, you would have maximum work from the work producing devices and you'll have least work consumed for the work consuming devices. Clear enough?
Yes, sir.
All right. Now, there are two kinds of reversible process. In an internally reversible process, there would be no irreversibilities within the system. That means during such process, a system proceeds through a series of equilibrium states. When the process is reversed, the system passes through exactly same equilibrium states while returning to its initial state. The system would come back to its original condition without having any irreversibility within the system. Quasi-equilibrium process is an example of internally reversible process, again with a frictionless piston. In an externally reversible process, there will be no irreversibilities outside the system boundaries. Let's see how. That means heat transfer occurring between system and surrounding due to infinitely small temperature difference is an example of externally reversible system. How? This is liquid water, and this is liquid vapors. So you have liquid water and liquid vapors in equilibrium. This is basically two-phase system. So any heat addition to a two-phase system until the system remains two-phase would be an isothermal heat addition. And you know that heat transfer through a finite temperature difference is a irreversible process. Isothermal heat addition, it's a reversible process, and you would say in both the cases. In one case, the energy is coming at 20.000001 degrees centigrade, and in other case, the heat is coming through a finite temperature difference. Within the system, if I look at the system, it's an isothermal heat addition. So the system is internally reversible. Both the systems are internally reversible. But when I look at the surroundings, when the temperature through which this heat is coming into the system, it's the difference between the system and the surroundings is infinitely small. I can categorize this as a totally reversible process. That means it is internally reversible and externally reversible also. But when I consider the heat transfer through a reservoir which is at a finite difference from the system, this is essentially a internally reversible process but not an externally reversible process. Reason being, heat transfer through the finite temperature difference between the system and the surroundings make it as externally irreversible process. Is this point clear to you?
Yes, sir.
All right. Moving on towards the Carnot cycle. So heat engines, they are at the cycle. If you remember, you had a pump over here, you had the boiler, then you had a turbine over here, and then you had the condenser. So you had basically four components. The initial cycle. In one part or process of cycle, work is done by the working fluid. So from boiler to turbine, the fluid gets heat and then it is used to produce work out. There is work out produced as a result of the cycle from 1 to, let's say, 3. And then from 3 to 1 back again from this for this cycle, there is work that is being done onto the fluid in terms of pump work. So there are two parts of the cycle. In one half, there is working fluid which is producing turbine work out, and in the other part, there is work done on the fluid in terms of work on pump, work by the pump, which is working. It says the net work out is difference between work output and work in. And so the thermal efficiency would be maximized by using process that produces maximum work during work output process and requires minimum energy during work input process. You remember that the energy that you're getting out of the system should be maximum and work in that you are giving to the system should be minimum. This should, and in order to do so, this can be achieved by performing all the processes through in a reversible manner. However, reversible cycles cannot be achieved in practice because of the irreversibility associated with each process cannot be eliminated. However, reversible cycles provide upper limits on the performance of real cycles. In short, The possibly best known reversible cycle is the Carnot cycle, which was developed in early 19th century by a French military engineer, Sadi Carnot, and the theoretical heat engine that operates on Carnot cycle is called the Carnot engine. We'll see what a Carnot engine is and how we can replicate it. We'll try to understand how we can rebuild the Carnot cycle. So Carnot cycle again is composed of four reversible processes, two isothermal and two adiabatic. If you remember the steam power plant, you had pump, you had a boiler, you had a turbine, you had a condenser. Heat was given into the boiler, QH, and condenser heat was rejected out of the condenser. As a result of turbine, work out was generated, and as a result of pump, there was work into the system. This is basically what was happening. Essentially, there are four processes: a boiler process in which heat is this is heat addition process, a turbine process, which is basically the work out process, a condenser process, which is basically heat rejection process, and a pump, which is work input process. Now, if I try to have these processes in order to develop a cycle, it says that in a Carnot cycle, it again consists of four processes. The first process is reversible isothermal expansion. Now, when a process is isothermal, you cannot have it as a finite heat transfer through a finite temperature difference. Since there is no temperature difference, dt is 0, you can call it as a reversible process, although the expansion is taking place. How this process is converted, let's say, again, you have some gas or some fluid within the piston at the temperature TH, and the piston cylinder assembly is essentially insulated from these two sides. Now, in order to the first process is resembling with the heat addition process. You have to add heat into the system. You have not insulated the back side of the piston, and you have brought this piston cylinder assembly close to an energy source which is at a higher temperature TH. Now, as a result of the expansion process, or as a result of this expansion process, the temperature would essentially decrease. अगर expansion होगी तो temperature क्या होगा system का?
Decrease होगा.
All right, it would decrease, but the decrease is catered by heat addition to the system QH, which maintains the temperature of the system as TH. So isothermally, there is expansion that is taking place within the system. Clear?
Yes, sir. Yes, sir.
All right. Now the system continue. This is the first process where heat addition is taking place. The second process is again the system continues to expand. From 2 to 3, the system is continuing to expanding, and you have insulated this side also. You have removed the reservoir and you have insulated this. As a result of this expansion from 2 to 3, the temperature would now go to a lower temperature, which is TL, and you call this process as reversible adiabatic expansion. The heat which is being generated is essentially contained within the system. So during this work, system does some work as the working fluid temperature decreases from TH to TL. These two processes, they are defined on a PV diagram. If I have this PV diagram, the first process, this is a the temperature line, the constant temperature line. From state 1 to state 2, my volume has increased, but the temperature remained constant as TH. Then from 2 to 3, I had this smaller temperature line, which is, let's say it is, or I'll draw it a little over here. This line is lower temperature line. So my system moved from 2 to 3 again. The system is expanding. But this time during the expansion, there was a decrease in temperature. So, all right. So this is TL. As my system moved from 1 to 3, this is essentially the area under the curve. That is the positive work generated as my system moved from 1 to 3. This is the work out of the turbine. So if you see, this work resembles the work generated as my system moved from the boiler to the turbine. So the first half of the cycle, this is essentially this is essentially the first half of the cycle. In the first half of the cycle, there is work generated and heat involved. So 1 to 2 heat was added to the system. 1 to 2 heat was added to the system, QH. So heat addition and work generation. So 1, 2, 3. During this process path, half of the cycle has completed. There has been heat addition to the system isothermally, and there has been adiabatic expansion. So there is work out which is generated as a result of this expansion. Half of the cycle, is it clear to you?
Yes, sir.
All right. Now, if we go back and look to the remaining half of the cycle, we start compressing it. Again, we have removed the insulation and we start compressing the system from 3 to 4. As we compress, we are doing work on the system. As a result of this work being done, the temperature TL would go up to TH. But we'll bring a sink which is at TL. So the additional heat that is generated would move out of the system in the form of QL. So if you remember, uh, now this portion of the cycle has started where QH is being removed from the system. Again, if you see, the process is taken place isothermally. Isothermally, you are taking heat out of the system so that your temperature TL remains constant. So if you see the cycle over here, this was your initial temperature line, high temperature line TH. This is your low temperature line TL. Your system moved from 1 to 2 and from 2 to 3. This is essentially your first half of the cycle. Work out generated and heat QH being supplied to the system. This is the first half of the cycle. Now for the second half of the cycle, the first process is where you have essentially moved from 3 to 4, and as a result of this movement, heat is being extracted out of system QL. The temperature still is TL. Then the process 4 to 1. You have removed the energy sink and insulated this side also. You continue compressing your system until your system comes back to the original condition and TL moves to TH. So you again complete the process by moving back to the fourth uh, position. This requires work input into the system, and this is being performed adiabatically so that all the heat that is generated during the process is used in making the system get back to its original condition. This is a reversible adiabatic compression process which increases the fluid temperature back to TH. Now, if you see, this is essentially the portion where your work uh, into the system is represented. The total area, this total area under the line 1, 2, 3, this total area represented the work generated. The area under the curve 341 is basically the region where you have supplied work to the system. This remaining portion, or the portion which is enclosed by the boundary of 1, 2, 3, 4, this region is essentially the net work which is produced out of its cycle. So the work net out is essentially the central region which is enclosed by these four states. Is this clear to you?
Yes, sir.
All right. Now, based on the Carnot cycle, you have developed two principles. These principles are very important to understand. The first principle, it says that these are called Carnot principles, and they are about the thermal efficiency of reversible and irreversible heat engines. By the way, if I ask you, do you expect the efficiency of a reversible heat engine more or an irreversible heat engine more?
Reversible, sir.
Reverse.
Reversible. All right. So I'll write over here. You are saying that efficiency of reversible heat engine is more than efficiency of an irreversible heat engine, obviously operating between same conditions. So it says the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between same two reservoirs. That means same TH and TL would have a reversible engine having higher efficiency as compared to the irreversible heat engine. Now, if I have to prove it, I'll prove it by assuming the other way around. I would say that, let's say I have a heat engine, one heat engine is irreversible. So the irreversible heat engine would have higher work output as compared to reversible. If I'll start with this assumption. There are two heat engines. One is reversible, the other is irreversible. So if you see, there are two heat engines. One is irreversible heat engine, the other is reversible heat engine. And I'm saying that they are operating between same reservoir temperature TH and TL. And if same amount of heat is being supplied to both, QH is supplied to the reversible one, QH is supplied to the irreversible one. I assume that if work of irreversible is more than work of reversible, is it possible or not? I am working on this assumption. So if you remember, work of a reversible heat engine or work of any heat engine is essentially QH minus QL. The lesser the value of QL, the higher would be the work. Is it clear?
Yes, sir.
Now, if I say that this reversible engine has high work output, work irreversible is more as compared to work reversible, what would happen to QL reversible as compared to QL irreversible? किसका QL ज्यादा होगा?
सर आपने कहा सर वर्क इरिवर्सिबल ग्रेटर देन वर्क रिवर्सिबल है
जी.
तो सर QL will be greater for reversible.
Yes. So it means if I say that, if I assume that work of irreversible is more as compared to work of reversible, which is less, QL irreversible would be less than QL reversible. Clear? Is this clear?
Yes, sir.
Now, let's say I am talking about the reversible heat engine. Let's say I am operating this heat engine in the opposite direction. That means there is work being, since it's a reversible engine, work is being supplied to the system. It is taking QL from the low sink and it is delivering QH to the high sink. So I am considering it as a reversible engine right now, working as a reversible engine. I can assume that since I have said that it's a reversible heat engine. Clear enough?
Yes, sir.
All right. So, and then I combine the, I say, irreversible heat engine plus the reversible refrigerator or heat reversible refrigerator or reversible heat engine, since it's working in the opposite way, since the cycle is opposite, I'll call it as a refrigerator. So if I combine these two together, this irreversible one requires QH. This rejecting, if I combine them together, this QH and QH would essentially cancel out. Clear?
Yes, sir.
So if I combine them together, combined heat engine plus refrigerator, QH that was moving out of the refrigerator essentially moved into the heat engine. So there is essentially no need of a high temperature reservoir. So I have removed that, and QH basically cancels out each other. So this is basically how we dealt with QH. The second thing we said that QL irreversible is less than QL reversible. So the direction of heat in this case would be which way? Upwards or downwards? पॉजिटिव डायरेक्शन क्या होगी? अगर हम दोनों को कंबाइन करेंगे, if we'll combine the heat QL out of the reverse irreversible heat engine and the heat being supplied to the reversible heat engine, if we combine them together, तो positive quantity क्या होगी?
Upward, sir.
Upward. Why? Because we had already assumed that QL irreversible would be less than QL reversible. So essentially the direction in which the heat would be flowing would be in the positive value would be in this direction. So QL reversible minus QL irreversible would be a positive quantity and directed upwards. Clear enough?
Yes, sir.
Now for the irreversible heat engine, it is producing work out irreversible. And for the reversible refrigerator, there is work in as work reversible. Now, what would be the net effect if we combine the two? Which is more?
Sir, irreversible, sir.
Irreversible is more. So the direction of irreversible would be followed, and you will have work irreversible minus work reversible as a positive quantity. Clear enough?
Yes, sir.
Is this clear? So far, is it clear? So far, is it clear or not?
Yes, sir. Clear, sir.
All right. Now, let's keep our focus to this combined system. What actually we are saying is that, let me redraw this combined system. Based on this combined system, if I redraw this combined system, what I am trying to say, I am saying that there is a engine X which is taking heat, some heat value QXL, whatever, I am just giving it a name, from a reservoir which is at a temperature TL, and all of this heat is converting into WXL some work. Do you think this is correct?
No, sir.
If you remember the Kelvin Planck's statement, there need to be a second reservoir where this heat has to be rejected. It is not possible to take in heat and produce work only without rejecting it to another reservoir. So this statement is in contradiction with the Kelvin Planck's statement. This means the initial assumption that we made, that the work irreversible is greater than work reversible, it is essentially not correct. That means the efficiency or the reversible work would be more than the irreversible work for the reservoir operating between two temperatures, two same reservoirs. Clear enough? Is this point clear to you?
Yes, sir.
All right. The second of the Carnot principle is that if there are two reversible heat engines, engine A and engine B, and the temperatures between which they are operating, TH and TL. If these temperatures, TH and TL, they are fixed, the reversible heat engines would have same efficiency. No matter what you do, they'll have same efficiency. That means the efficiencies of all reversible heat engines operating between same two constant temperature heat reservoirs would have same efficiency. This is a very important principle. Now, there is a derivation involved. I'll not go into the derivation. I'll just give you a brief overview. If you want, you can go through it. It's very simple. In case you know you want me to go through it, I'll cover it up later. But it's not essential. The conclusion of the derivation is very essential. I'll just give you a brief overview. It says the clause's second principle. It says that the efficiency of a reversible heat engine, it is dependent upon a function of TH and TL. Since we said that whatever TH and TL, if these two are constant, whatever heat engine, reversible heat engine you have, the efficiency would remain the same. That means efficiency of a reversible heat engine is function of the temperature of the reservoir and the sink, the source and the sink. Clear? So there is some function G, which is a function of TH and TL, and the efficiency of a reversible heat engine is dependent upon the efficiency of on the function of TH and TL. Clear? Is this clear so far?
Yes, sir.
By default, you know that the efficiency of any engine is essentially 1 minus QL over QH. Efficiency of a heat engine is dependent upon this. Now I can say that efficiency 1 minus efficiency is essentially QH over QL, or I could convert it into the fact that QL over QH is essentially 1 over 1 minus efficiency, anything. So again, the the only thing that is important is QH over QL. If efficiency of a reversible engine is function of TH and TL, that means QH over QL for a reversible engine is also a function of TH and TL. Although not the same function, some other function f, but QH over QL is also a function of TH and TL, some other function, whatever the function. I'll not go into the detail of that. The closest function that has been found, or the simplest function that has been developed for QH and QL, this function f that we say it's a function of f, it essentially QH over QL for a reversible heat engine is function of the temperatures of the two reservoirs. This is a very important aspect for the uh, efficiency determination of a Carnot engine. So for a reversible heat engine, the ratio of QH to QL is equal to the ratio of the temperature of the reservoirs from which the QH and QL are interacting or deduced. So Carnot heat engine, any heat engine would have an efficiency of 1 minus QL over QH. This is basically the efficiency of any heat engine, whether reversible or not. For a Carnot heat engine, which provides the upper limit, that is the reversible heat engine, the efficiency is 1 minus TL over TH. So if you have a reservoir at 1000 Kelvin and a low temperature reservoir at 300 Kelvin, the reversible heat engine would have an efficiency of 70%. Irreversible heat engine would have any efficiency less than 70%. And a heat engine having an efficiency of 80% is essentially impossible. So now you have an answer of, if you don't have 100% efficiency for a heat engine, how can you determine the maximum efficiency that is achievable for a heat engine? For heat engine operating between 1000 to 300 Kelvin, it cannot have efficiency more than 70%. So it says if your efficiency is less than that of the efficiency of a reversible heat engine, It's an irreversible heat engine, that the actual heat engine. If it is equal to that of the reversible engine, it's a reversible heat engine, which is obviously not possible. And the efficiency, if it is greater than the reversible heat engine efficiency, it's essentially impossible. Similarly, for the I'll go for the refrigerator. I'll quickly go through this example. It says that you
सर
have
क्वेश्चन
G, G, G.
सर आपने जो कहा कि 70% से ग्रेटर नहीं हो सकती तो ये तो टेम्परेचर पे डिपेंड करते हैं मतलब TH और TL पे अगर
तो सेवेंटी
टेम्परेचर
परसेंट
रेशियो
तो इसी के लिए तो कहा है जो
रिवर्सिबल
1000, जो heat engine 1000 or 3, an engine that is operating between 1000 and 300 Kelvin, it can have a maximum efficiency of 70%. So if you
ओके
say
सर
that the engine would have an efficiency of 80%, that is not possible. This is what I'm trying to say. Clear enough?
ओके सर
So you have a heat engine. This is a Carnot heat engine. Carnot heat engine is ideal or reversible heat engine operating between 652 and 30 degrees centigrade, and the heat provided to the system is 500 kilojoules. You have to determine the thermal efficiency. When you say thermal efficiency of Carnot engine, it is basically the reversible efficiency. The amount of heat rejected to the sink per cycle. Now, remember that whenever you have to use this form of efficiency, the Carnot efficiency or the reversible efficiency, you have to use 1 minus TL over TH, and the temperatures are in absolute scale. Remember this. So you will convert them into absolute scale and you'll find that the answer is 0.672. That means 67.2% of this heat energy could be converted to work at max. That is the maximum. The remaining has to go to the low temperature reservoir. It could be more, but the certainty is that you cannot have more than 67.2% of this heat converted into work. Now, what is the amount of heat rejected to the sink per cycle? Again, you know that for a reversible heat engine, QH over QL, reversible is essentially equal to TH over TL. You just have to plug in the values QL, sorry, TL, TH multiplied by QH would essentially give you the heat that is rejected in the form of QL, 164 kilojoules. All right. The Carnot refrigerator and the heat pump, essentially the same principle. Any refrigerator or heat pump, this would have the coefficient of performance in the form of QH over QL, and similarly QL over QH for heat pump. For a Carnot refrigerator or heat pump, the COP of heat pump, which is reversible, you'll have the ratio in the form of TL over TH. And for the reversible refrigerator, it would be in the form of TH over TL. So this is essentially for Carnot refrigerator or heat pump, or ideal refrigerator or heat pump, or a refrigerator working on reversible cycle. The efficiencies or the coefficient of performance are dependent upon the temperatures of the source and the sink. Again, coefficient of performance for a refrigerator operating between 300 Kelvin and 275 Kelvin. A reversible refrigerator could have the coefficient of performance is 11. Irreversible refrigerator would have again 11, and an impossible refrigerator would have the coefficient of performance of 13. Now, an inventor claims to have developed a refrigerator that maintains the refrigerator space as 35 Fahrenheit, and by operating in a room where the temperature is 75 Fahrenheit, and the coefficient of performance of this refrigerator is 13.5. You have to verify this claim. Simple thing, determine the maximum possible coefficient of performance for the refrigerant, which is 1 over TH over TL minus 1. You plug in the values, you see that the coefficient of performance comes out to be 12.4. So what do you think? It's a reasonable claim or not?
No, sir, not reasonable.
Yes, it's not reasonable. Anything greater than 12.4 as a coefficient of performance is not possible. The last thing that we have to discuss today is basically the quality of energy. Quality of energy, we say that this is the efficiency of a Carnot heat engine or a maximum efficiency achievable for a system operating between two temperatures. Now, let's say the fraction of heat that can be converted to work as a function of source temperature, if you want to see that. If I keep my low temperature as constant 300 Kelvin, and if I start changing the high temperature reservoir temperature, the temperature of the high source reservoir from 925 to 350, I see that the efficiency of my system decreases from 67.2 to 37.4. This means that more of high temperature thermal energy can be converted to work. If 500 kilojoules of heat is provided to this reversible heat engine, if the energy is provided to the heat engine at 925 Kelvin, more than 50% of this energy would be converted into work. But if the same energy is coming from a reservoir which is at 350 Kelvin, it would be less than one fifth of this energy that would be essentially converted into work. The higher the temperature of the thermal energy, higher is its quality, more of the work it can generate for you. Is this clear to you?